This is Chemical Processes for Micro and Nano Fabrication. I'm Chris Mack, the professor for this class, and we're at Lecture 59, Lithography Double Patterning. As we saw before, there is a resolution limit, which for the case of the pitch is a hard limit. As of today, 2013, we are using a wavelength of 193 nanometers, and we do not have a lower wavelength option available commercially at the moment. We'll talk about EUV lithography and its possibilities in an upcoming lecture. The highest numerical aperture we have available today is 1.35 for immersion lithography. And again, there doesn't seem to be anything on the horizon, at least in the next 5 years, to enable that numerical aperture to be larger than 1.35. And for dense patterns of lines and spaces, the value of K1 in our LELE resolution equation has a hard cutoff of 0.25. As a result, the resolution given by this LELE equation here is 0.25 times 193 nanometers divided by 1.35, which is 36 nanometers. This is the minimum half pitch that can be printed. That means the pitch is 72. But in reality, it's virtually impossible to achieve that minimum. We can get it with, say, an alternating phase shifting mask and or dipole illumination if we use purely coherent illumination, but we can't do that. We have to use sources that have certain sizes of spots. So the practical half-pitch limit is in the 38 to 40 nanometer range, which gives a minimum pitch in the 75, minimum pitch of 75 to 80 nanometers. This is the smallest you can do with a single lithography step in manufacturing today. The problem is we want to do better than this. And we've been at this limit for several years. These 1.35 NA tools came out 3 or 4 years ago. And we want to keep moving, keep progressing down to smaller features. So, how do we do that? Well, one option is double patterning. This hard cutoff resolution limit is the limit for a single lithography step. But if we print twice, we might be able to do something better. Let me try to illustrate. The limit, remember, in our imaging is the minimum pitch that I can print. So if I print a pattern of lines and spaces, there's a limit to how small this pitch can be. But there's no limit, hard cutoff limit anyways, to how small I can make the individual lines. So for example, if I overexposed or if I use some kind of a trim process with a plasma etching to shrink these lines down, I can actually print lines that are much smaller than the minimum half pitch. So if the minimum half pitch is about 40 nanometers, I might be able to print lines that are more like 20 nanometers. So a 20 nanometer line with a 60 nanometer space, line 20, space 60, and pitch would be at its minimum of 80. Then I could come back with a second lithography process, printing again small 20 nanometer lines on an 80 nanometer pitch, but now shifted by half of the pitch off to the side. By taking these two patterns and interspersing them, I can get a net result of half of the pitch. Therefore, the new limit would be about a 40 nanometer pitch instead of an 80 nanometer pitch. This is called double patterning. And there's a lot of difficulties in making this work, but it's not a fundamental difficulties, but practical difficulties. Let's look at more detail on how we might do this kind of double patterning. And I'll talk about one particular style called Litho-Etch-Litho-Etch. As the name implies, we're going to do lithography and then etch and then do it again. So the first thing we do is lithography. We have the pattern, the substrate here, the pattern, the material we want to etch above it, and then something called a hard mask, which I'll explain in a moment, just above that. Coat with photoresist, we expose, we develop, and we form our pattern. And we form it in such a way that we're at the minimum pitch, but we've made the lines narrower than the spaces. This is the first lithography step, litho 1. Then I'll transfer this pattern with an etch step into the hard mask. So the hard mask, as the name implies, is going to be used as a mask for subsequent processes, but its main characteristic is that it is thin and it has very good etch resistance for our subsequent pattern transfer processes. So we perform an etch. This is the first LE of our LELE process. Litho and an etch, strip the photoresist, and what do we have? We've got patterns at the minimum pitch, and we've made the line widths smaller than half of the minimum pitch. In fact, they're about a quarter of the minimum pitch. Now I coat with a second resist and image new lines and spaces. This time you can see that they're shifted so that they're about in the middle of this larger opening between my hard mask patterns. So I do a second lithography step. It's also at the minimum pitch, and we also make these lines about 20% of the, 25% of the pitch. So what do we do next? We use this combined resist hard mask combination as an etch mask for the underlying layer. So we perform our second etch. Second etch, followed by stripping of the photoresist, gives us this pattern. We could strip the hard mask or leave the hard mask on depending on our needs, and we would have what? Patterns where the minimum pitch is half what I could do for any single exposure, thus breaking the resolution limit. If the minimum pitch I can print with a single step is 80 nanometers, the minimum pitch I could achieve with this double patterning Litho-Etch-Litho-Etch would be about 40 nanometers. Here's some examples. These were done at IMEC, industry consortium in Belgium that does leading edge device and lithography research and development. And you can see from the pictures the two different lithography steps. So the different shadings, one is the hard mask and the other is the photoresist. And you can see how we've interspersed one pattern inside of the other. But we can make more complicated patterns as well, so you can see how we can in fact take an existing design and cut it up into two pieces where one piece is printed in one level and another piece is printed in the other level, and then they mate, they join together to form a more complicated pattern. Here you show how they form combining one litho level with another litho level to get these smaller pitch patterns. You can also see how complicated it can get. You can see how difficult it is to prevent, say, pinching that happens at these spots, etc. Here's a cross-section showing the hard mask and the photoresist after it's been etched into the underlying layer. So this is possible to do, but it is not easy. There are problems with LELE, Litho-Etch-Litho-Etch. For example, cost. Well, we're doing litho and etch twice. So we have essentially double the cost of a single patterning operation. Well, this is not good. We like to keep our costs low. Doubling the cost is a bad trend. Overlay. Remember that if I go back to this picture, I have to do a lithography step on the second level right in the middle of the first level. The problem, it's hard to get exactly the middle. We get some error. In fact, if you look closely, you might see that this photoresist line is a little bit closer to the hard mask on its right versus on its left. If you look at the gap width, that the gap width on the right is a little smaller than the gap width on the left. That's because of now the high sensitivity to overlay errors. We can control line width easier than we can control overlay, but now with LELE, overlay errors between the two patterns translate directly into critical dimension errors. The error in the gap width is a direct function of the overlay error. This means we have much tighter requirements on overlay control than we have in single patterning. And this has been very difficult aspect of LELE, and has required dramatic improvements in the overlay capabilities of our lithography tools. Then we have to do pattern decomposition. If we have a complex pattern, we have to break it up into pieces so that one piece is done in one lithography and etch step, and a second piece is done in a second lithography and etch step. Well, not every pattern is so easily decomposed, and so our software to automatically do that has to be able to handle these difficult situations. So LELE can be done. It is hard, but we're working on it, and in fact using it in commercial production today. Another approach is called self-aligned double patterning. It's a very different way of doing double patterning. We start what looks like the same way. We do a lithography and an etch, and here we have what I called the hard mask before, but I have a pattern that has been etched into a layer. The resist has been stripped, and so now I have the minimum pitch, and for each feature I have about 25% of the pitch. So we've done the first litho and etch, just like in the Litho-Etch-Litho-Etch process. I'm going to call these dummy patterns, or mandrels, and we'll see why in just a moment. Next, though, instead of doing another lithography step, this is what I'm going to do. I'm going to deposit some material, or maybe even grow some material, which will cover everything, in particular the space between the lines. These are going to create what we'll call spacers, because we'll do an etch back process. That is, after we've deposited everywhere, we'll etch it back everywhere, and you can see that there's a certain thickness in the open areas and there's a certain thickness above the lines, but at the sidewall, by the nature of how this coating process works, the thickness of this spacer material is much greater than anywhere else. So if I do an etch process that etches everything straight down, and I wait until, say, the middle of the space hits the substrate, and then I stop, this is the kind of pattern I'll have left. I'll have etched away everything except for a little piece on the sidewall of the mandrel. That's called a spacer, or a sidewall spacer. So this is also called the sidewall spacer approach to double patterning. So what do I have? I still have one pattern on the same pitch, but now every line that I've made has these sidewalls built onto both left and right sidewalls of the original pattern. Here's the key step. I'm going to strip that dummy pattern right out of the middle. The dummy pattern is made out of one material. The sidewalls is made out of a different material. I put it in some etchant that will remove the material right out of the middle, the mandrel. And what's left is just the sidewall spacers. But now look, I have a sidewall spacer. I have a feature for every sidewall. I have twice as many sidewalls as I had features to begin with, so now I have twice as many features. And their pitch is half the pitch of the original. If I then use these sidewalls as an etching mask to etch into the underlaying layer, I have now a pattern with a pitch of half of what it was before. So like before, if I print at the minimum pitch of, say, 80 nanometers, the result is a pattern with a pitch of about 40 nanometers. This is called the self-aligned double patterning. It's self-aligned because every sidewall is self-aligned to its neighboring or partner sidewall on the other side. Here are some images that I got from Applied Materials. Here I show the mandrel in the middle and the two sidewalls on either side. Here is what it looks like after I've etched out the mandrel in the center. That's why we call it a dummy pattern, because it disappears eventually, and now I have twice as many patterns. And when I etch that into the etch stop layer below, a hard mask or something below, this is what it looks like. So again, I can create a final pattern with half the pitch. Let's take a moment and look not in cross-section, but at top-down on what this SADP process looks like. So after we've done the first litho and the first etch, suppose we're printing 3 lines as shown here. So these would be the mandrels, the dummy patterns, and then when we create the sidewalls around each of these, you know, in cross-section it looks very simple. I get a feature for each sidewall, feature for each edge, and that's how I double the number of features. But when I look top-down, I see something else happening. At the ends of the lines, I also get the sidewall being deposited, so that every time I have a line, it turns into a loop. Well, maybe I don't want to make loops. Maybe I want to make lines that come to an end. These loops will always form at the ends of each of the mandrels, which means if I want to create an arbitrary shape, I'm going to have to do a second lithography step and etch step simply to trim off the line ends where I don't want them. So this self-aligned double patterning process in some respects is very simple and easy. In other respects it has some serious complications. First of all, this is the cheapest of the double patterning approaches. There's only one critical lithography step where I make the first pattern. It's usually at high resolution, and the control of the CD in particular is very, very critical. But there's only one, and so this makes this step, this process cheaper than a litho-etch, where I have 2 critical lithography steps. For overlay, the overlay requirements are not much different from single patterning, because I'm not trying to intersperse 2 individual lithography steps. So I don't have those problems. However, we have some strict design rule requirements. Note that every feature I make is the same line width. I'm building features on the sidewalls. Every one of those line widths is determined by the thickness of the material being deposited, the process of etch back, etc. But I only get one line width. Every feature has the same line width. I can't arbitrarily make whatever sizes I want like I'm used to doing in normal lithography processes. That means I can only use the self-aligned double patterning process for very restricted conditions. Often those conditions will be appropriate. In particular, in memory, we see designs of cell arrays in NAND flash and in DRAM chips where we always want the same feature size everywhere, so this is not much of a problem. But for logic, it can be a big problem. And then finally, there's going to be 1, sometimes 2 trimming steps required to trim off the loops and to create these whatever exact pattern shape that I want, which isn't always easy to figure out how to do. And therefore there's some interesting automated design tool requirements as well. It's currently in widespread use. The SADP has been the first double patterning approach to be used in manufacturing, and it was used by the flash manufacturing guys, people. It's still in use. We have taken flash down to 20 nanometer half pitch using sidewall double patterning, self-aligned double patterning. And it works very well. So there's no doubt, there's a proof of principle that it works quite well for memory applications. Maybe it will be useful in logic at some point in time, but so far the logic designs have not been amenable to this style of double patterning. However, There is another approach called complementary lithography. Here I use some kind of a method of creating small lines and spaces. I could use dipole illumination so that I can get pitches down to the minimum, or phase shifting masks, and produce, say, 80 nanometer pitch features at the limits of 193 lithography. Or maybe I can even use something like self-aligned double patterning and print smaller pitches. But this produces an array of lines and spaces. What I'll do then is the complementary lithography. So creating arrays of lines and spaces, even for very small pitches, is relatively easy to do. But I generally don't want just lines and spaces to make a circuit. I want patterns that have other characteristics. One of the things I often want to do is create lines that are shorter than some other line. So I can use a second litho and etch step that essentially is perpendicular to these lines in order to trim the lines and make cut patterns into these lines. Something like this. A lithography step that etches away a region in the middle of these lines. So now I have some longer lines and some shorter lines. This, it turns out, can be very useful in logic patterns. Intel, for example, has been using this style of complementary lithography since the 45 nanometer node. Here's an image from one of their 32 nanometer node chips where they've taken, I believe this is looks like the poly gate level, where they've taken their poly gates and printed long lines and spaces and then cut them, as we see at the ends, but also cutting them here in the middle to create the gates of the dimensions that they want, some long, some short. Notice that in this approach, they'd have to design their chips so that all the gates are pointing in the same direction, and all the gates have the same width, and all the gates are spaced apart from each other in the same way. That is, there's one pitch. But given this restricted design rule, where we put all of our transistors on a grid, then this complementary lithography approach is probably the easiest way of doing double patterning. And it works quite well given the restrictions of the designs. So we've seen now three basic approaches for double patterning: a Litho-Etch-Litho-Etch approach, a self-aligned double patterning approach, and then a complementary lithography or line trimming, line cutting approach to double patterning. Well, let's review. What have we learned in Lecture 59 on double patterning? You should be able to quickly and easily answer these questions. What is the current resolution limit of single patterning? Name 3 double patterning approaches. What are the main advantages and disadvantages of each double patterning approach? And finally, here's an essay question. So I don't expect you to quickly and easily answer this question. In fact, I did not talk about this in the lecture, but I think maybe you have enough information after listening to this lecture to think about this question. So here's my essay question. Do you think that there might be a future for quadruple patterning? What's quadruple patterning? Well, it would be double patterning applied twice. This would enable cutting the pitch in half again, for example. So if we had 80 nanometer pitch getting cut to 40 nanometer pitch with double patterning, what about cutting that 40 nanometer pitch down to a 20 nanometer pitch, 10 nanometer half pitch? Is that possible? Is that practical? Why or why not? So that's your essay question for this lecture. Next time we're going to talk about EUV lithography, a potential way of reducing the wavelength so that we can avoid having to use double patterning. Till then.